Okay, so welcome once more. So let me just share the slide. So ICH 413, Petroleum Refining Processes, week 5. Today we're looking at secondary or product improvement processes. Secondary processes, otherwise called product improvement processes. Production of liquid product streams by distillation, that we saw direct distillation of crude oil, or by cracking processes. It only it gives some few products that sometimes might not be directly marketable, and so you will need to carry out some other processes on such products to bring it to marketable liquid products. So, and then there are several steps you can take to do this. So we have several other unit processes that are involved in the production of final products. Such processes may be generally termed secondary processes or product improvement processes. These secondary processes, they are not carried out directly on the crude oil. It's the products or the fractions of the primary crude oil distillation that are used for secondary processes for the improvement of the product. So in addition, that term product improvement includes processes such as reforming processes, which the molecular structure of the feedstock is reorganized. The feedstock is not useful for immediate use, and so you reorganize the structure to be suitable for the final product that is required. Example is conversion. Reforming process is a conversion process where the molecule is rearranged. Example of that, N-hexane restructured or rearranged to cyclohexane, or cyclohexane rearranged to benzene. So this processes reform or rearrange one particular molecular type of compound to another one, therefore changing the properties of that product to what is suitable or what is required. So these secondary processes, they help to expand the range of products that we can obtain from petroleum. So with the high demand of high octane gasoline, so we need to carry out the secondary processes to be able to improve the octane number of gasoline and improve the octane number of gasoline by improving the properties of the compounds within the boiling range fraction of gasoline. For instance, we have straight run gasoline. That's the one that is distilled directly from the crude oil. They have very low octane numbers. So any process that will be useful to improve the octane number, it will help to meet the demand for the high octane number gasoline that is required these days. So we have such process as thermal reforming. It's a reforming process, but thermally, which was developed and widely used but to a much lesser extent than thermal cracking. We have talked about thermal cracking, catalytic cracking. So now we're talking of cracking, of course, is breaking down. Now we're talking of reforming, which is rearrangement of the structures of the compound. So thermal reforming was just a natural development from the existing thermal cracking processes. While cracking converts heavier oil into gasoline, reforming converts or reforms structures of those compounds that are within the gasoline into higher octane gasoline. The equipment for thermal reforming essentially is the same as that of thermal cracking. Only difference is that the temperatures, one of the differences is that the temperature is much higher. So we have here platforming and reinforming. The first one is reforming. We're talking about reforming. So, and under reforming, we have thermal reforming, which I just talked about now. And then we have platforming and we have reinforming. Those are three types of reforming processes. The platforming and reinforming are both catalytic reforming processes. Thermal reforming, as the name implies, is just thermal reforming, while these other two are catalytic reforming processes. So the reinforming is what we're looking at now. It uses a fixed bed regenerative reforming system method. And in this case, of course, we're using catalyst. So we're using rhenium and platinum combination as catalyst. So, and this also helps to give good fouling resistance, removing the odor. And it can be operated at a pressure below 20 atmosphere. Fixed bed, continuous catalytic reforming, it can be classified into two types based on the catalysts that are used. One is a cyclical regenerative process, which uses non-precious metal oxide catalysts. Second one is cyclical regenerative process, which uses platinum alumina catalyst. In both cases, they both use what is called swing reactors. Swing reactor, of course, the reactor is where all the process takes place, the reactions. And so what we mean by swing reactor is that you have two reactors. One reactor is operating while the other one is waiting. And then when the catalysts are deactivated in the reactor, in the operating reactor, you now swing to the other reactor and use, while the former one you're using, you reactivate that catalyst inside that one while you're using the other one. So one will be operating and one will be already ready, waiting for use after reactivation of catalyst. So the cyclic regenerative fixed bed operations using platinum catalyst is basically a low pressure process between 250 to 350 pounds per square inch pressure. And this gives higher gasoline yield because you're not doing too much cracking reactions, and also it gives higher octane products from a particular given naphtha. So, and naphtha, of course, is the aliphatic straight run compounds. So, and then it gives also better hydrogen yields because it's doing few cracking. So whatever is cracked, hydrogen is produced because of more dehydrogenation and fewer hydrocracking reactions. what it does, it doesn't crack much, it's few cracking, and then more hydrogen is removed, and so you have excess hydrogen yield. And so the coke that is yield, that is carbon, that is yield, in this process, the carbon is produced, that is the coke, that is what is deactivating the catalyst, because the coke keeps on depositing on the catalyst until it gets it deactivated, it's no longer useful. So the coke yield, in this case, that its attendant catalyst deactivation, increases rapidly because of the low pressure that is used in this process. So now platforming, the second one, that is catalytic reforming, just like the ring forming. The first step in the platforming process is the preparation of the feed, of the naphtha feed. So the feed is distilled. First thing is to distill the feed, separate to different fractions. The fraction, you pick the fraction within the boiling range of 120 and 205 degrees centigrade. Then sulfur, actually sulfur is one of those compounds that poison catalysts, which we will soon see. So naphtha fraction may be treated to remove sulfur compounds. Then otherwise, during the process, the hydrogen-rich gas, of course, you have seen that within this process, a lot of hydrogen is produced because of low cracking and then removing of hydrogen. So the hydrogen that is produced it has to be scrubbed free of hydrogen sulfide content. That's the preparation. So the prepared naphtha feed is heated to 455 degrees centigrade, between 455 to 540 degrees centigrade, and then it is passed into a series of 3 catalyst cases under pressure of 200 to 1,000 pounds per square inch pressure. So then further heat is added to the naphtha between each catalyst cases in the series. We say we have 3. So you add heat to the first one where the reaction is taking place, and then when you move to the next one, you add more heat. So the material from the final catalyst case is fractionated into hydrogen-rich gas stream and to reformate stream. Reformate are the products that you obtain from this reforming process. So, and the catalyst that is used composed of this sized 1 to 8 inch pellet of alumina containing chlorine and about 0.5% of platinum. Okay. Now, catalyst poison removal. I mentioned to you that as you're using the catalyst, coke is forming onto it, that is the activation. And apart from that, there are some metals that normally will poison the catalyst and render it not useful enough. So catalyst life is limited as much by physical breakdown as well as by deactivation. Sulfur is the main catalyst poison, and the catalyst poisoning is theoretical. It can be reversed, with the catalyst then being restored to near full activity by steaming. Of course, steaming it, you will remove the carbon and leave the catalyst free. So in practice, the activation may cause catalyst to overheat and coke to the point that it must be replaced. That is along the line. At the final stage, after activating, reactivating, it can finally end up that you have to replace a particular catalyst. So reforming catalysts are also very sensitive to poisoning by heavy metals. So it's sulfur that can poison the catalyst. Heavy metals also can poison the catalyst, although much rarely in low boiling hydrocarbon feedstocks and in naphtha feedstock. Okay. So the latest technique developed by the refining industry to increase gasoline yield and the quality is to treat the catalyst from the cracking units to remove metal poisons that may accumulate on the catalyst. So removing this will help the catalyst to function well, and then the gasoline yield and the quality will increase. Nickel, vanadium, iron, and copper compounds contained in catalytic cracking feedstock are deposited on catalyst during the cracking operation, thereby adversely affecting both catalyst activity and selectivity. The increased catalyst metal contents affect catalytic cracking yields by increasing coke formation on top of it, and then decreasing gasoline, butane, and butylene production, though it ends up with increasing hydrogen production. So we have some recent methods that are used for catalyst poison removal. This particular one is a recent commercial method that was developed and adopted for catalyst poison removal. One is called DMET. DMET, you can see DMET, MET for metal. A cracking catalyst is subjected to two pretreatment steps. First step affects vanadium removal. The second affects nickel removal to prepare the metals on the catalyst for chemical conversion to compounds. What you do this, you now have to remove these metals by getting it into the form that can be removed by water. And so treating it to the form that can be removed by water, and then you use water and wash off that compound from the catalyst. So the treatment steps include the use of sulfurous compound followed by chlorination with anhydrous chlorinating agent. So, and then this will convert it into a form that water can wash, and then wash it with aqueous solution of chelating agents. Of course, your aqueous solution will now wash it off because it's in the form that can be moved. Water, that water can be active in removing the metals. The catalyst is then dried. The catalyst that you have already washed, cleaned off the metal poisons, is then dried, further treated for returning to the cracking unit. Like I told you, the swing reactors. After treating it like this, while the other reactor is working, now you've done it well, now it's okay, it goes back to the cracking unit, and the other reactor that has the activated catalyst will now be left for the treatment of removing, and then while you use this other one that is ready. Okay. Now the other method, the second method, is METX. This process consists of cooling, mixing, ion exchange separation, filtration, and resin regeneration. So let's see how it is done. So moist catalyst from the filter is dispersed in oil and returned to cracking reactor in a slurry form. You're mixing the catalyst in oil. So on a continuous basis, catalyst from the cracking unit is first of all cooled. It's coming out from the cracking unit hot. So you cool it first, then transport it to a stirred reactor where you mix it with an ion exchange resin. So the catalyst resin slurry, now you mix the catalyst with the ion exchange resin. It's now a catalyst resin slurry. This then flows into a luterator. A luterator is a device that separates particles into groups based on their size, shape, and density. So a luterator will now do the separation. So the catalyst slurry is taken overhead to a filter, and the wet filter cake is slurried with oil and pumped into catalytic cracked field system. The resin leaves the bottom of the luterator and it's generated before returning to the reactor. The resin leaves the bottom of the luterator. So, and now let's look at isomerization. This is a catalytic reforming process that provides high octane constituent in the heavier gasoline fraction. But the normal paraffin, this is the other processes I explained to you, they can provide high octane constituents using heavier gasoline fractions. But you cannot do this using paraffin components of lighter gasoline fraction. And so in this case, isomerization comes to play, where you now use your normal butanes, normal pentanes, hexanes, and so on that have poor octane ratings. So the conversion of these normal paraffins to their isomers, that is the isomerization, yields gasoline components that are of high octane rating in the lower boiling range. So conversion is obtained in the presence of catalysts, alumina chloride activated with hydrochloric acid, and it's essential to inhibit side reactions such as cracking and olefin formation. So basically what we're aiming to do is isomerization. So the present isomerization applications in petroleum refining are used with objective to provide additional feedstock for alkylation units or to improve the octane number. So straight chain paraffins like normal butane, normal pentane, and normal hexane converted to their respective iso compounds by continuous catalytic processes. So the natural gasoline or light straight run gasoline can provide feed by first fractionating as a preparatory step. You have high volumetric yields of above 95% and 40% to 50% conversion per pass. That is, once another pass is another one, and so on. When you're carrying out isomerization processes, isomerization reaction. Importance of isomerization in petroleum refining are twofold. First of all, it converts butane into isobutane. So this one is now alkylated to liquid hydrocarbons in the gasoline boiling range. You alkylate it. The second one is that the process is used to increase octane number of paraffins boiling in the gasoline boiling range. So it's twofold. One is to help produce, alkylate the products, and you improve the yield. And then the other one you improve the octane number. Process involves contact with hydrocarbon and a catalyst under conditions that are favorable to good product recovery. Okay. The catalyst may be aluminum chloride promoted with hydrochloric acid, or it can be platinum-containing catalyst. Both of them are in either case, they're very reactive. And because they are very reactive, they can lead to undesirable side reactions along with the isomerization product. So these side reactions include disproportionation and cracking. Disproportionation can happen, also cracking can happen as side reactions. And this help to decrease the yield of what we are looking for and produce olefinic fractions that may combine with the catalyst and shorten the life of the catalyst. So side reactions are not really desirable. So these undesirable reactions are controlled. You can control these undesirable reactions by carrying out inhibitions. So you add inhibitors to the hydrocarbon feed, or you carry out ion in the presence of hydrocarbon. So you inhibit the side reactions, adding inhibitors. Okay. So paraffins are readily isomerized at room temperature. Reaction is believed to occur, that isomerization, by the formation and rearrangement of carbonium ions. So the chain initiating ion, alkyl R plus, is formed by the addition of proton from the acid catalyst to an olefin molecule. So you can see the R plus there. So which is the proton added to the olefin molecule, which may be added. Then regular more molecules are added. Present in some impurities that can be formed also by dehydrogenation of the paraffin. So except for butane, isomerization of paraffin is generally accompanied by some side reactions involving carbon-carbon scission, breaking of the carbon-carbon bond, when catalysts of aluminum halide type are used. So it's a schematic representation of isomerization using an aluminum chloride. I don't think I want to spend time on this. You will look at this later. Okay. Earliest important process was the formation of isobutane, which is required as an alkylation feed. The isomerization may take place in the vapor phase with activated catalyst supported on a solid phase, or it can take place in liquid phase with the catalyst dissolved in it. So if it takes place on the vapor phase, you support it with solid catalyst. But if it takes place in liquid phase, then you dissolve the catalyst in it. So a pure butane feed is mixed with hydrogen to inhibit olefin formation as a side reaction. And it is passed to the reactor at temperature of between 110 and 170 degrees centigrade at the pressure of 200 to 300 pounds per square inch. Product is cooled, the hydrogen separated, the cracked gases are then removed in a stabilizer column. The stabilizer column product is passed to a super fractionator, and then the N and the isobutanes, they are separated there. So with pentane, equilibrium is favorable at higher temperatures than that of butane that we have seen. Operating at the conditions of 300 to 1,000 pounds per square inch pressure, because temperature is higher instead of that compared with that of butane. This one is higher, between 240 and 500 degrees centigrade in case of the pentane on. Okay. Modern catalytic cracking processes. We have different catalytic processes like fixed bed process, fluid bed process, and moving bed process. My time is running because I have another meeting very soon. That's why I was trying to see how we can have this earlier. So in fixed bed process, the catalysts in the form of small lumps or pellets we placed in layers on beds in several catalysts containing drums called converters. So those catalysts containing drums, if you put the catalyst in form of pellets or layer by layer, then feedstock vaporized at about 450 degrees centigrade, less than 7 to 5 psi pressure, and pass through one of the converters where the cracking reaction took place. So we're still talking of fixed bed process. After a short time of carrying this out, the position of coke on the catalyst will render the catalyst ineffective. And then using a synchronized valve system, the feed stream return into a neighboring converter. You remove the feed stream to another converter while the catalyst in the first converter is regenerated. That's what I was explaining about the swing converters. So after 10 minutes, catalyst will be ready to go on stream again from the other swing converter. Fixed bed processes have generally been replaced by moving bed or fluid bed processes. So fluid bed catalytic process is another one. We just looked at the fixed bed. We have fluid bed catalytic cracking. We have fluid bed catalytic cracking unit. We have orthoflow fluid bed catalytic cracking. We have shell two-stage fluid bed catalytic cracking. We have universal oil products fluid bed catalytic cracking. Those are the processes we have under fluid catalytic processes. I will want you to go and look at those ones, the different catalytic cracking fluid bed processes. Okay, and these are the different fluid bed processes, and we also now have moving bed process. We have the different types like airlift, thermophore catalytic cracking process, that's fluid moving bed process. We have hydroseed catalytic cracking process also. This is moving bed, of course. Then we have hydroflow catalytic cracking process as another one of moving bed. We have suspensoid catalytic cracking as another one of moving bed process. I think I'll have to end it here, end the lecture here. My lecture has ended. The last part of the lecture, we're looking at catalytic cracking processes. We look at fixed bed, and we look at fluid beds, different types, and we look at moving beds, different types. So we have to end the lecture here. I'll get back to you because my other meeting is starting a moment now. So I'll stop sharing, and we're leaving the live streaming now. So thank you, and we'll see you. We'll do some revision. We'll revise and see. In case you have any need, you can ask me question at any time.